Hello, everyone. Thank you very much for your patience. I apologize. We are ready to get started. We had a little technical challenge this morning. My name is Matthew, and I work for the astronomy department at the University of Arizona, and I'm one of the course instructors. I'm going to say thank you to Alexander for all of his technical help with us today and hand this right over to Professor Impey.
Okay, welcome everyone. Yeah, we occasionally have little technical difficulties. Also, we're taking a little larger than usual gap. We've been going every week, but as you might imagine, with 40,000 students, unclear whether they're returning my campus, a faculty member's life is pretty busy right now, so we have to spread things out a bit. There's only so much time in the day, but the floor is open for your questions.
Excellent, thank you very much. The first question is from Nick, who sent an email. Nick's question is about neutrinos. Given that the vast majority of neutrinos pass straight through normal matter, where do they go?
It's a good question. So where do they come from might be the other part of the question. Where they come from, I'll answer that first, because is that they are almost equally abundant to any fundamental particle, the most dominant fundamental particles in the universe, which is to say that there are roughly equal numbers of neutrinos, electrons, and protons and neutrons in the universe, especially protons and electrons, which is why people have wondered if they could be the dark matter, since dark matter outweighs normal matter. So if neutrinos had mass, it would really be very meaningful. So neutrinos have been around since the Big Bang because they're created in high energy interactions. For instance, an antineutrino is released every time beta decay happens, which is the decay spontaneously of a free neutron, isolated neutron, with a half-life of about 11 minutes. So there are natural processes in physics that lead to the production of neutrinos and antineutrinos, and they're very abundant, and they've been in the universe literally since the Big Bang. They are what is called, if they were dark matter, they were what is called hot dark matter, which is to say most of the neutrinos at the time they were produced had relativistic velocities close to but not at the speed of light. And so these are flying through the universe at close to the speed of light. And when we try to detect them on Earth with a detector that's typically underground to shield it from all the other particles that are out there and cosmic rays and other charged particles that come from the sun or from high energy sources around the galaxy, we have to shield a detector from all those stray signals. And so because their limited interaction means they pass through, the classic example is you could have a sort of 1,000 kilometers of pure iron, an iron bar, and a neutrino could pass through the length of that 1,000-kilometer iron bar with a modest chance of interacting on the way. That shows how low the probability is for an interaction in the typical low density of matter. So the only way they can be detected, given that they travel at almost the speed of light, they can't really be captured in any way, is by very rare interactions with normal matter. Either a glancing interaction, literally a collision, or a high enough energy interaction that leads to the production of other particles, or perhaps a flash of light in a solid state detector. So these are the ways neutrinos are detected, and you just have to create a quiet environment for other signals, and then you have a chance of capturing these fleeting particles. And it's a very important part of the agenda of not just high energy physics, but also astrophysics, to understand the properties of neutrinos in the universe.
Excellent, thank you. The next question is from Malik, who's on with us live, who would like to know, can we explain what time is?
Not really. Time still has mysteries. Probably the most dominant aspect of time that everyone wants to know about is why does it flow in one direction? In physics, most interactions or types of physics occur equally in each direction. In other words, if you see a particle interaction occur in the lab in the forward direction of time as we observe it, it's possible for that reaction reversed in time to also occur naturally. In other words, particle interactions do not seem to observe any time asymmetry. And in all the searching and experiments they've done, physicists have only been able to find extremely subtle and a handful of instances where time reversibility does not occur in physics. So we have fundamental physics that's largely time reversible, and yet we have the overwhelming and inevitable impression that time moves in one direction. We get older and die, the Earth gets older, the universe evolves, everything around us is part of a time arrow that moves forward. So that is the fundamental and profound mystery of time. Now, people have tried to explain this by appealing to basic physics, of thermodynamics, of perhaps connecting it to entropy or the number of disordered states a system might have, where there's a general thermodynamic trend towards disorder. And maybe it's the trend to disorder in the laws of thermodynamics that overlays the psychological aspect of time on our lives and the universe. That's a plausible partial explanation, but it doesn't fully unravel the issue of time. So I would say it's fair to say that time has mysteries that still survive. I'll also note that in general relativity, Einstein coupled space and time explicitly in his equations. So the bending and distortion of space that's caused by gravity in our understanding of gravity through general relativity also occurs to time. So time in the laws of physics through Einstein is a supple quantity. Now it still moves in the forward direction as we perceive it, but the rate at which it moves is dependent on the local circumstances.
Excellent, thank you. The next question is from Oyan Sarkar, who would like to know, why can't gold atoms be created in our sun?
Gold will not be created in our sun simply because our sun is not massive enough to create a high enough temperature at any point in its life to fuse gold atoms. Gold typically doesn't even occur in the normal late evolutionary stage of a star like our sun. Our star is a main sequence star, which is turning hydrogen into helium by the fusion method. And in principle, fusion can make very heavy elements, including gold. But because gold is a heavy element above the stability plateau represented by lead, the most stable element, it requires energy input to make gold. And that energy input in a star typically comes in a supernova phase or in a violent explosive phase of a star. And the sun will have one brief violent phase, and that's when its core collapses and it, meanwhile, it jettisons a shell of hot gas and turns into a planetary nebula near the end of its life. But that violence and that temperature that's created is by far insufficient to make gold. Essentially, you need instantaneous temperatures of billions of Kelvin to create gold, and that typically only happens in a supernova explosion or extremely violent explosion in the universe. So gold is made throughout the universe, but typically during the violent late throes of the death phases of massive stars.
All right, another thing that's been in the news lately is the NEOWISE comet that a lot of people are seeing. So people would like to know if you could talk about comets, the NEOWISE comet, and if you have seen it.
It's been in the Arizona skies, and we've had people that work at our local observatory, the Catalina observatories, which are incidentally shut due to a raging fire we've had north of us that's consumed 150,000 acres, I think. So it's been hard for our telescopes to look at it, but we've amateur astronomers and people with small telescopes have got beautiful pictures, and they've been sharing them online just as recently as this morning. I haven't seen it. It's in the early morning sky now, and it's been monsoon pattern in southern Arizona, so we've had a lot of clouds. So I haven't seen it personally. I've seen pictures from my colleagues. It's a spectacular comet. It's a comet that has a near-Earth trajectory. It passed fairly close to the sun through the inner solar system, and then now is headed on its way out and giving us a little show before it heads out. News stories, of course, have speculated about the odds of it hitting the Earth. Those odds are incredibly small. It's not coming very close to the Earth at all. And even if it were, people who calculate trajectories can very accurately predict the odds of a collision. And since this comet, I think, is estimated to be 5 kilometers across, it's a pretty small object. That's enough to do a lot of damage, of course. And the Earth is a small planet, and space is vast, so the odds of a collision for any particular pair of comet and planet are very small.
Excellent. Thank you very much. The next question is from one of our emails. Mega would like to know, can acceleration due to dark energy rip apart a star or some other kind of interstellar object?
So I think the questions relating to the possibility of dark energy to accelerate the expansion of the universe to the point where it rips apart normal matter. This is called the Big Rip scenario. Now, the Big Rip, as it's been called colloquially in the press, is a very particular hypothesis for dark energy. It's the hypothesis where dark energy has the property that it increases with time, and that leads to an exponential expansion of space-time. And the cusp of that exponential works its way down in scales to the point where galaxies are ripped apart by dark energy, and then stars, and then planets, and eventually atoms, and that's the end of everything. So a star being ripped apart is basically part of this chronology, that if dark energy has this particular property of exponentially growing in strength. We don't know much about dark energy. However, we see no sign in what we do know about it that it has the properties that would be required for the Big Rip scenario. So while the universe is indeed expanding at an increasing rate, so there's an accelerating expansion, it's not an exponentially increasing expansion to the point where it rips apart stars or normal matter or humans themselves.
Okay, thank you very much. The next question is from Richard, who would like to know, why is it that the Big Bang theory is so widely supported, and what other theories are being or have been proposed?
Well, historically, the main alternate to the Big Bang was called the steady state theory. So in the 1940s and 50s, there were seriously considered arguments for a steady state universe. So people knew about the expansion. The Hubble expansion was detected in the late 1920s. And so the galaxies are moving apart. And the steady state theory maintained an eternally unchanging universe by just essentially postulating that matter was spontaneously created at what amounts to a very small rate in the vacuum of space, and that eventually aggregates into new galaxies. And so you can have galaxies all moving away from each other and all moving apart in an expanding universe where it looks the same with cosmic time, and new matter is created to fill the vacuum as the old galaxies move further apart. So that was appealing to some people who didn't like the idea of a Big Bang where everything is created instantaneously out of nothing. But the evidence eventually was persuasive in favor of the Big Bang. So the steady state was discredited not overnight, but in a series of discoveries in the early to mid 1960s mostly. So the pivotal one was the discovery of the microwave background radiation. That was a prediction of the Big Bang. It was predicted in the late 1940s by George Gamow, famous physicist, emigrated from Russia to the United States. And he predicted there would be a low temperature radiation bath left over from the early hot dense universe. That signal would not be present in the steady state model. And when it was detected by accident in 1964, that was very persuasive evidence for most people that the Big Bang was the correct theory, because it's very hard to explain that radiation anyway. And in the methodology of science, when you have a theory that predicts something very concrete and specific that's hard to explain any other way, and then you find it, that's a very powerful affirmation of a theory. The other two affirmations of the theory, beyond the Hubble expansion itself, which had been known for decades, were the fact that the helium in the universe can be explained by mostly having been created in the first 3 minutes after the Big Bang. When the universe itself was millions of Kelvin and hot enough to fuse hydrogen into helium. And you can explain the universe being roughly 1/4 by mass helium that way and not any other way. So that was a second very strong piece of evidence in favor of the Big Bang. And so those calculations were done in the early 70s. So really, for 25, 30 years now, the Big Bang has been the preeminent theory. And there are truly no very different alternatives. There are modified versions of the Big Bang, of course, but there are no fundamentally different alternate theories at this point.
All right, thank you very much. The next question is from one of our live viewers. Is dark energy increasing? So this is from Jatin Chopra, who would like to know, is dark energy increasing, and if so, by how much?
No, dark energy is not increasing. If you measure the strength of dark energy in any particular region of space, some metric size, it's the same. However, the space, its positive energy, or its positive pressure, if you like, negative pressure actually, is causing the space to expand. So in the sense that space is diluting and the strength of dark energy stays the same, you could say in that sense that dark energy is increasing, and because it's just continuing to cause space to get larger and larger. But the strength, as we measure it astronomically, the strength of dark energy over cosmic time or in any direction of space has not been found to vary.
All right, the next question is from one of our live viewers. Richard would like to know, I understand that gravity is one of the 4 forces in the universe, but do we know any more about gravity or what causes gravity?
What causes gravity is an interesting question. I mean, it's a fundamental question. We have a good theory of gravity, general relativity, and we know, as the question alludes to, that there are 3 other fundamental forces: the electromagnetic force and the weak and strong nuclear forces inside the atom. And so gravity takes its place among a set of forces in nature. There are only 4, and the relationship between them is really unclear, and that's probably a big mystery of gravity, because people hope, physicists hope, that there is one underlying uber force or ultimate force that somehow eventually combines all those 4 separate forces. And so the confidence that that's the case comes from the fact that the 2 nuclear forces, the weak nuclear force and the electromagnetic force, have been shown to be aspects of the same thing back in the 1970s at CERN. And there are hints that the weak and strong nuclear forces and the electromagnetic forces are versions of the same thing, and that would be a grand unified force. So there's confidence from that history that gravity will eventually be unified into some super explanation of gravity that includes all the other forces of nature. And it wouldn't probably look like general relativity theory at all. It would be some fundamentally different theory, maybe string theory. But we haven't made much progress towards that. So it's a hope and a confidence among some physicists that it can be explained with a superior theory eventually.
All right, so the next question is from Subham Gosavi, who sent an email. Are we able to travel in space by using mineral-rich asteroids, and how would we be able to control the direction and speed of one of these asteroid spaceships?
There are sort of 2 separate questions there. One is, can we use asteroids as sources of resources for space travel? And the answer, I think, is yes. The reason we would want to do that, actually, is important to say, why would you want to? Why would you bother? The Earth has a lot of resources. Well, the resources on Earth have to be lifted out of the Earth's gravity, and it costs a lot of energy to do so. So eventually, if we're going to travel in space and through the solar system, routinely and at modest cost, we actually have to probably build our spacecraft in 0 gravity or out beyond Earth orbit, and certainly power them and fuel them that way. And so in that sense, an asteroid could be a useful repository. For example, asteroids have a lot of metals and minerals in them, or precious metals, rare earths. Some of them have frozen water in them, and they have basically the ingredients for rocket fuel, as well as the ingredients for making rockets themselves, if you could mine those materials and turn them into useful products. So in a sense, asteroids do represent a hope for space travel, in the mid-future, let's say 50 years from now, not 10 years from now, probably. And so yes, I don't think we would actually turn the asteroid into a spacecraft. I mean, we definitely could attach rockets, powerful rockets, to an asteroid and steer it. Changing its direction in other than a limited way would take an enormous amount of energy, because asteroids are very massive, have a lot of momentum. So I don't think asteroids will actually be turned into spaceships in that sense.
All right, the next question is from one of our email participants, and the question is, oh, I'm sorry, I kind of lost my place here. If the universe is, so this is basically about the radius of the universe. If the universe is 13.7 or 13.8 billion years old, and the radius of the observable universe is roughly 46 billion light years. Doesn't that mean that the universe has been expanding faster? Can you talk about how that affects the speed, or how the speed of expansion affects what we can see in the observable universe?
Right. So naively, if the universe was 13.8 billion years old, as we think it is, there are several good measurements of that, and the fastest things can expand is at the speed of light, then you would imagine that in any direction there would only be a distance of 13.8 billion light years until the edge, and so that would be the radius, and the diameter would be twice that number. Instead, we see a radius measured through a model, and in terms of the farthest objects we can see, that's 46 billion light years. So that's 3 times as much, and a diameter twice that number, 92 billion light years. And the answer is indeed that the universe, for certainly the first third of its history, was expanding faster than light. And after that, it decelerated, and then more recently it started to accelerate again. So that phase of superluminal expansion, especially early on when the universe was really expanding very, very rapidly and was being decelerated by the dark matter and normal matter. The acceleration and the speed between any 2 points in space moving apart was multiples of the speed of light, several times the speed of light. At the time of the microwave background radiation, for example, any 2 points in space 400,000 years after the Big Bang were moving about 40 times the speed of light away from each other. So really high multiples of the speed of light, superluminal, and that of course leads to the fact that now, after a lot of superluminal expansion early on, the horizon, or the edge to which we can see, is more than just the edge of the universe turned into light years.
Excellent. Thank you very much. The next question is from one of our online participants. Noel James would like to know, can you please explain the different types of quarks?
Sure. So the quarks are the components, the subatomic components of neutrons and protons, and they can also combine to make other intermediate mass particles called mesons. So quarks are baryons in the high energy physics terminology, which means the heavy particles, as opposed to electrons and neutrinos, which are leptons or light particles. And there are 6 flavors of them. They are all fractionally electrically charged, which is a very big surprise and a shock, in a sense, to physicists who are used to a proton with 1 positive charge, an electron with a negative charge, a neutron with no charge. So having fractional positive and negative charges, fractions of a third, basically 1/3 and 2/3, and minus a third and minus 2/3, that was a big surprise. It also means that they have to combine to make particles with integer electric charge. And so a neutron and a proton each consist of a triplet of 3 quarks held very tightly together. In fact, the quarks are essentially never seen isolated. It's extremely hard, even with an accelerator like the Large Hadron Collider, to liberate a quark for more than a tiny fraction of a second. So the neutrons and protons, the conventional matter of the universe, are made of the first 2 quarks to be discovered, up and down. And these are also the lowest mass quarks. In the 1970s and 80s, a second generation of quarks was discovered, and they were given in more eloquent names by physicists of strange and charm, or S and C. They're abbreviated usually by letters. These are more massive quarks. They're unstable. They tend to only combine to form exotic particles that don't live very long, and so that's why it took a long time to discover them. And then the final triplet of quarks is called the top and bottom quarks, and they're more massive still. They were produced in accelerators. Actually, isolated bottom quarks, I think, were not produced until fairly recently, just a few years ago. They've now all been studied in various combinations. And so there are these, the quarks come in pairs, but there are 3 families of the quarks, different mass ranges. And it's part of the agenda of high energy physics to understand why there are 3 generations of quarks. Why does nature need 6? And why are they in pairs and have different mass ranges? And that's an unfinished agenda of high energy physics to explain that.
Okay, the next question is from one of our live viewers. Kendra Smith would like to know, do you consider astrology a science? At one point, astrology and astronomy were entangled. And what do you consider the origins of astronomy?
Absolutely. Astronomy and astrology were entangled through the Renaissance, and most of the major players in the scientific revolution in astronomy concluding Copernicus, Tycho Brahe, and in particular Johannes Kepler, who's a great mathematician, but he was practicing astrology. He actually earned his living that way for quite a while. So through that period of time, pretty much up until Newton's time, astrology and astronomy were twinned. And that wasn't to say that astrology was ever scientific. It's always been lacking a basis in scientific fact, but it was a practice that started with the Romans. So the Romans, and I think even some earlier civilizations, they were interested in divination, as they called it, which is divining human affairs or predicting the future based on telltale signs. And since the stars and planets and the reasons why they're there and why they move were not understood in antiquity, naturally a supernatural explanation would arise that somehow the planets and stars and where they were at our birth and through our lives controlled human affairs and influenced our personality. So the astrology originated thousands of years ago, and it was indeed not separated from astronomy right through the 16th century into the 17th century. Thereafter, however, science became modern. I'd say with Isaac Newton, we declare the beginning of modern science. And at that point, astrology is widely recognized by the scientists of the time to be not valid as a scientific pursuit because it does not have predictive power and there's no physical explanation for why astrology's claims should be valid at all. And in the modern era, it's gone back into the pop culture, sort of the way it was with the Romans 2,000 years ago. And no practicing astronomer, thinks that astrology has anything valid to say scientifically.
The next question is from a live viewer. CCC Laptop would like to know if there are such things as brown or black stars.
Yes, in both senses of the color term. There are brown dwarfs, and people use that term to refer to very low mass objects which are below the fusion limit for a star. So if you have a big ball of gas and it's below about 8%, the level is just under 8% of the mass of the sun, then even though gravity will make it hot in the center, it will never be hot enough, which is to say it'll be under about 1,000,000 Kelvin, for even the feeblest fusion reactions to occur. And the feeblest one is from 2 hydrogen atoms making deuterium. So if even deuterium fusion cannot occur, you have something that's just a very hot cloud of gas, and it's not formally a star. And technically, and sort of colloquially to astronomers, that's called a brown dwarf. And I don't know if it actually occurs brown in the sky. I don't think we see them physiologically as brown, but that's just to indicate that it's an extremely dim star that is not shining by in a source of emission for fusion reactions. Brown dwarfs fade because if the gas cloud is just collapsing and radiating heat into space, it will gradually cool. And so the final fate of a brown dwarf is, you might say, to be a black dwarf, which is a gas cloud that emits no visible, no detectable radiation at all. It's decayed in its temperature down to the level of the microwave background, or a few degrees Kelvin above absolute zero. And at that place, it's essentially indistinguishable from the darkness of space, and so it will be a black dwarf.
The next question is from Yogahara Haran, who would like to know, can you please explain and talk about the mechanism of core bounce in a supernova?
Right. So in the last stages of the life of a massive star, after it has reached the most stable element, which is the sort of, it's created iron 56, so it's made fusion occur up to iron. Thereafter, no energy is obtained from fusion reactions. Energy has to be put in to make fusion go, and so that's a dead end for fusion. And at that point, however, so there's no new energy produced once you get to iron. It's a sort of the pile up at the end of the road of the fusion chain. And however, the gravity still exists, and so the star goes into a very violent collapse. It's a massive star, so this collapse occurs very fast, and essentially a free fall time by gravity. And that creates enormous compression as the mass is falling in radially of a very large and massive star. And the material is piling on top of itself, if you like, just crescendo of gravitational collapse. And what happens is the material at the center has nowhere to go, and it essentially reaches close to a point, and so some of it will bounce back, and on the way back, it meets the material that's still falling in. So the core bounce occurs when the first material to fall in has nowhere to go and just sort of rebounds, and then that's the core bounce. And then when that rebounding material hits material still falling in at close to the speed of light, that collision creates enormous temperatures. That's what creates the multi-billion degree temperatures that can create the heaviest elements in the universe. So the core bounce is a phase of the destruction, the detonation of a supernova that eventually leads to an incredible amount of radiation, the creation of heavy elements, and then nebula or glow that can last for millennia.
The next question is from one of our live viewers. Astrogate asks, how would Mars Perseverance, or really any other robotic probe, be able to detect life on Mars? How can it tell if it's 100% biological, if it's alive or dead, or how would it detect non-carbon-based life? Like, how do we look for life on Mars?
Yeah, the Mars rover, Perseverance, is the next Mars rover delayed from its 2020 date. It was Mars 2020, the mission. Now it's 2022. The launch window slipped by one Mars cycle of orbit. It is touted as a life detection experiment, but the expectations are rather modest because the ability to do life detection remotely on another world with a small instrument package is very difficult. If we could bring a sample back to the Earth, we could scrutinize it with a huge lab's worth of equipment that we could never get to Mars. So what Perseverance, not all its instruments are doing this. Some are doing geochemistry, some are just taking pictures. So there's a range of instruments on Perseverance. The couple of life detection experiments, so to speak, are looking for our heavy, using spectroscopic methods, or vaporizing material sometimes, or reflectance spectroscopy, to look for heavy organic compounds, and in particular to look for the heavy organic compounds that are prime ingredients of life, and that can go beyond simple amino acids to sort of complex carbohydrates and other fundamental ingredients of life. What the instruments are not doing, however, is something that directly tells you whether you're looking at nucleic acid-based life as we have on Earth. That would require something like a polymer chain reaction PCR machine to try and tease out fragments of DNA and then multiply and amplify them up so that they're easily detectable. That's what a PCR machine does. We're looking at situations on the surface of the Earth, of Mars, where the life it cannot be alive. It's too cold and low density. So these would be fossilized potential microbial forms dating back millions and perhaps even billions of years to when Mars did have surface water. And so it's very indirect and it's very elusive kind of evidence. It's not going to be a slam dunk to say that there's life there. And we can't put it in a petri dish, we can't reanimate it. There's a lot of things we simply can't do. And as to the question of non-carbon-based life, big question, important question, we're not looking for that at all. There's only so much you can do with one of these rovers and its limited instrumentation. And to look for something that's not carbon-based would require a lot of speculation as to what the metabolism was, and then very particular instruments designed around detecting those alternatives. But since we don't know what the alternatives are, there are many of them, and each one would require separate instruments. You can see that it becomes a nightmare to try and design a non-carbon-based life detection instrument because we simply don't know what the diversity and range of possibilities are. So Perseverance is doing something a little more modest, more limited, easier to interpret. I don't think it'll disappoint us, but it won't answer the fundamental question of whether there's life on Mars that's like life on Earth.
The next question is kind of an amalgamation from several different participants. Lots of people are interested in time travel. So is it possible? How is it possible? Some people are wondering if going faster than the speed of light could help you travel in time. So can you talk about time travel and our current views on that?
So the current verdict from physics is fairly simple and a little disappointing. The verdict from physics is that time travel, which is to say being able to move fluidly backwards and forward in time is simply not possible. It violates the laws of physics. And that has been tested at the level of subatomic. We don't have to worry about people doing this. You start with simple fundamental particles where you can do all sorts of experiments and make them go very fast to the speed of light, close to the speed of light. And there are no indications that we can make acausal physics happen in accelerators or lab experiments. So disappointingly, there's no indications in particle physics or fundamental physics that time travel is possible at the level of particles. And if it's not possible at the level of particles, by extension, it's not going to be possible at the level of people. So that's the disappointing answer. So the best we can do is, because time is a supple entity, as we know from general relativity, it's not time travel, but we can imagine experiments where we cheat time, because if you travel at somewhat close to the speed of light, which itself is a different trick involving a huge amount of energy, but not violating a law of physics, then you can create a situation where a fast-traveling astronaut or Voyager has their physical and biological clocks that they have on their spacecraft slow down, as seen by a distant observer or the place they originated. And so in that sense, you can cheat time. And so there are hypothetical experiments. It's called the twin paradox, where twins are born on the Earth and one makes a relativistic voyage in space and returns to a much older twin who's not gone to such high speeds. So the relativistic travel creates some interesting ways to distort time, but not cheat it in the sense of moving backward and forward. And probably to finish, the fundamental objection to time travel in physics as we understand it, and physics is pretty sturdy, it passes its tests every day in labs around the world millions of times essentially. The difficulty of time travel in physics is that it would mean acausal events. So science depends on events that happen that have identifiable causes. And if you scramble that logic, that events that you see have causes that you can identify, you actually upend science as we know it.
All right, the next question is from one of our live viewers who would like to know, do galaxies have life cycles like stars of birth, life, and death?
In a sense, yes, galaxies have life and birth and death. They definitely evolve because they're made of stars, and stars evolve. So there are populations of stars, and they can evolve. So galaxies evolve in a number of ways. First of all, in our model of how the universe grew as it expanded and how objects formed and evolved in the expanding universe, we have a sense of hierarchical structure formation where smaller objects eventually combine to form bigger objects. So it's very sure, in the case of our own Milky Way, we can see it happening even now, that the large galaxies in the universe were built from smaller pieces over cosmic time. So galaxies evolve in that sense. They evolve by having been built from smaller subcomponents early in the universe. And we can see that process continuing. It slowed down that process in the life cycle of a galaxy. The building and the merger phase was most active about 10, 12, maybe to 8 billion years ago, and it's gone at a much more sedate pace now because, of course, the universe has got bigger and the average space between galaxies is increasing, and so interactions and mergers are less likely and happen less often. So the active phase of galaxy construction is long past, and it's now quietened down. Meanwhile, galaxies do still interact from time to time, and that changes the way they look, so that's part of their evolution and part of their phases of their life, birth, and death. And then looking forward to the death of galaxies, they do have a life cycle in that sense too, because they're made of stars, and all stars have finite lifetimes, so eventually and logically, every star in any galaxy will eventually die. The lowest mass in the stars in the galaxy have the longest lifetime, so things just above the brown dwarf boundary, 10th the mass of the sun, live hundreds of billions of years. But if you play time forward, then all galaxies in the universe are eventually going to go dark. And then if you go even beyond that, beyond trillions of years to a many larger factor than trillions of time, galaxies actually start to dissipate. They dynamically dissipate. And so the stars that have been held together by the gravity of the normal and dark matter eventually evaporate into space, so galaxies dissipate. And so they become dark and then they dissipate in the future. So they absolutely have a life cycle.
The next question is from Pashupati, who sent an email. Why is Vega, the star Vega, and a source of active research among astronomers, or is it? And if so, what are they studying?
Well, Vega's of interest to astronomers just because essentially all the bright and luminous stars in the night sky are of interest because we can get such exquisite data on them. I mean, obviously any star that you can see with your naked eye, if you look at it with a 1 or a 10-meter telescope, you're going to grab enormous numbers of photons. So what that means is you can look at a star like Vega in detail with telescopes, and you can look across the electromagnetic spectrum. You can detect it in X-rays and radio waves and things that for normal stars would be hard to detect because it's very bright. It's not that close. It's not one of the nearest stars, Vega, but it's a very luminous star. So we've got unprecedented depth of information about Vega. Also, it's a star where we've been able, or some years ago, using the infrared capabilities on the ground and the Spitzer Space Telescope, we're able to see that it as a young-ish star, we can see the leftover material from its formation. So Vega's given us insights into how planet systems form around stars. Also, because it's close enough, we can inspect that material. So for those are just a set of reasons why a star like Vega, although it's not special of its kind, of its mass, it's not an age, it's not a particularly special star, its proximity plus its luminosity means we have extraordinary level of information about it.
The next question is from Jim McLeod, who would like to know, for gravitational lensing to have good resolution, does the density of the dark matter cloud that's doing the lensing need to be extremely smooth?
Can you just rewind to the beginning of the question?
Oh, I'm sorry. Gravitational lensing, for gravitational lensing to have good resolution, or for us to use gravitational lenses to see things, do the dark matter clouds or objects need to be extremely smooth?
Not necessarily. In fact, that question leads to an important part of how gravitational lensing works and is used. Essentially, we're reversing the logic of the question. So we're using the observation of lensing in the universe to infer properties of the dark matter, because we don't know what the dark matter is, and we don't even always know how it's distributed. So in the case of a background galaxy or a quasar, say, that's being lensed by an intervening galaxy, the way the lensing occurs, the relative brightness of the different components in the lens system, the shear that might be applied to them, variability as it maps differently between the different sight lines, all of this gives us information. And so the best gravitational lenses, not all of them can be used this way, but the best ones actually give us physical and very essential information on dark matter, and allow us, for example, to test the hypothesis that the dark matter is smoothly distributed. Now, we expect that it will not be, because the dark matter theory predicts that dark matter does clump just as normal matter does, not as dramatically as normal matter. And so, for example, the halo of our galaxy is not completely smooth dark matter. It's dark matter with subclouds and concentrations. It's lumpy. And if that is the case in general, then that will show up in gravitational lensing, because occasionally when the sight lines in the lens system pass through clumps of dark matter as opposed to just a very low density region, it amplifies the light by more. And so by looking at the amplification pattern of gravitational lenses, people have done work to look at the clumpiness of dark matter in galaxies far away. They do it statistically. You typically, from one lens, you learn very little, but if you have a dozen or half a dozen that are similar type, you actually start to learn a lot. And that work is very important and difficult work that's been done in the last 10 years or so. And it has shown convincingly that the halos of these massive galaxies causing the lensing of more distant objects are indeed clumpy. The dark matter is clumpy, and we can measure the nature of the clumpiness. And it's an important piece of information about dark matter and its nature.
All right. The last question is from Shakila Ramasamy, who would like to know, what is the biggest object in space ever discovered? And this is going to have to be our last question for today so that we can make it to things on time here.
right? The largest thing ever discovered, well, there's a little argument about this from time to time, but basically the largest things ever discovered are superclusters of galaxies. So clusters of galaxies like the Virgo cluster and the Coma cluster, things that are fairly nearby in the universe, are part of larger concentrations of galaxies. We, for example, are part of something called the local supercluster, which is 50 million times about 100 million light years on a side. It's not a spherical object. Now, there are superclusters. There's a couple that compete for this, and I can't remember their names. They have slightly obscure names. But the largest superclusters that have been identified anywhere in all the galaxies catalogs are of sizes about 300 to 400 million light years across. So that's roughly the largest size of any object in the universe. And that's pretty much the largest size you expect, because gravity has not had enough time to coalesce any larger object in the history since the Big Bang. So if a bigger object than that were discovered, it actually would be a problem for our cosmological model. So appreciate the questions covering comets to cosmology as usual, and we'll be taking a couple of weeks break and we'll be back with you. Thank you, and thanks to Matthew and Alexander.
Yeah, and I just want to mention two things before we sign off. One is that we have a Discord server that we have set up, and that's it. The link is in the description. And so if anybody is interested in that, please check that out. The other thing that I wanted to mention is somebody asked if you could see the comet from Arizona, and the answer is yes. I actually was able to see it 2 nights ago in the northwest sky in the evening, just after like an hour after sunset, underneath the Big Dipper. And then, as Chris mentioned, we can see it in the early morning, but that will be in the northeast part of the sky. So thank you very much, and we will talk to you all in 2 weeks after we take a short break.